Hello. Now we are going to demonstrate the microstrip patch antenna simulation. It is our company Akademika lab solution from Mumbai. Today's problem conception is basically the microstrip antenna, which is very much popular now in these days. This is we called as an RMSA antenna, rectangular microstrip antenna. Here we can see this rectangular shape on the FR4 substrate. This antenna we are going to be simulated with the help of one simulation software called as an EM Cube. The model name is EM Picasso, which is more popular for the microstrip devices. The problem conception is to simulate the RMS antenna, the first, then observation of the E field creation on microstrip structures. The next observation of the far field and its comparison with the practical far field data means the radiation pattern which is simulated by the software, and we are going to compare with the practical one. Also we are doing the parametric study of the RMSA. Mainly in the RMSA antenna, the critical factor is the feed point. If you vary the feed point, your return loss parameter it get vary. So in this case, mostly the people are conscious or candidate are conscious to optimize your feed point. Also, the mostly the people also vary this the width sides to optimize this the cross polarization level or XPD level. But in this demonstration, we are showing the parametric study as well as the field distributions over the patch antenna on the different heights. Here is the EM Picasso. This is the more popular model of the EM Cube, which is mostly relevant for the microstrip structures. This is mostly the planar structure simulator for modeling and designing printed antennas and planar wave microcircuits. And the main facility is the layer periodic structures. The layer periodic structures is important, as you seen in this diagram. The first layer, second layer, third layer, fourth layer, and the fifth layer, and the sixth layer, and many more layer you can simulate with the help of this EM Picasso. EM Picasso is backed by the 2.5D full wave method, that is the more popular methods in the microstrip, that is called as a methods of moment, and which will generate the results like a surface current, return loss, VSWR, Smith chart, and your many more results with the help of methods of moment. Also, it can handle the structures like of arbitrary number of metal layouts, slot traces, vertical interconnects, and lump element intercept among the different substrate layers. So here you can see the structures also, the blue color or the green color, the antenna is there. This is a multi-layer antenna, multi-layer stacked multi-resonator antenna, where the one antenna is buried in the dielectric, and the upper layers the some patches are there which will enhance the directivity. At the same time, the bandwidth enhancement is possible by using such kind of structure. So the multi-layer environment simulation is possible with EM Picasso. Now we are coming to our design problems. The design of the RMSA, we are referred by the book called as a broadband microstrip antenna. The author is KP Ray and Dr. Girish Kumar. And in this book, they are recommended the this kind of rectangular microstrip structures. And here we are demonstrating the antenna, which is an infinite ground plane substrate. Here you can see this is the patch, as well as this the outer is the ground structures. And now this is the length is the first function, second function is the width, and the third function is the X position from the center, that is the feed position mostly. Here you can see the height of that substrate as well as the epsilon r. So here is the we are recommended the parameters. The frequency is 2.4 gigahertz, which is an ISM band frequency. We are utilizing a FR4 substrate, 1.6 mm thickness, or we can say this is the 1.6 mm height. PEC is the at the both side. The full ground is the PEC, upper side is also PEC. We are considering length is 29 mm, width is 38 mm, and the ground size is 90 mm by 90 mm. As I told, as that is an infinite ground substrate bed antenna to show you results. Then a probe position, which is a 7.25 25 mm, which is at this location, and y is 19 mm. Still we need an optimization, because if we as per the design formula, if we fit it and this position, we are not getting a good return loss or impedance matching. So we required an optimization, that also we are demonstrated by our colleague Mr. Vinayak Nikam. He is demonstrating the software with us. Now we are going to be start the software, and our friend Vinayak Nikam will demonstrate the software. So Vinayak, start.
Thank you, Anirudh sir. Now you can see this is a EMCube software icon. Now I am double click and start the EMCube software. Okay. So you can see the windows of EMCube software. Here is the main toolbar. Here is a lots of options for antenna drawing, and you can see here is a five such options provided by EMCube. Now I am selecting the EM Picasso. You can see here is the last one is the EM Picasso options. I am selecting this. Then you can see this is a browser project browser window. Now I am minimizing all these options. First you can see the pop-up window stack up setting. Here is stack up setting which is required for uh, uh, antenna material. Now I am closing this window. After some time you can we are providing that setting. Okay. Now I am just telling you the steps of the designing of a patch antenna. Here you can see the one option. This is a unit. I am clicking that unit, and you can see unit is millimeters and grid spacing is 5. Then press OK. Then I am all the settings of the length and width and all that settings should be in width, should be in millimeter. Okay. Next option is a frequency. Then you have to press the center frequency of the operating antenna. Now I am pressing the center frequency is 2.4 gigahertz and bandwidth is 1 gigahertz. Okay. Next option is materials. Here you have to add the substrate material, substrate epsilon, substrate mu, and now I am showing the how to add the substrate. Okay. New, then press new, create new material. Okay. Here I am entering new material name. I am entering FR4 underscore Akademika. I am entering epsilon r values is 4.2. Specify loss tangent should be 0.09. Then I am pressing OK. Then after that OK. Now I have to select the layer stack up which is included in computation domain. Okay, I am just right click on layer stack up and layer stack up setting. Then you can see the pop-up window which is include top half space, layer 1, bottom half space. In a patch antenna there is a bottom half space which is always ground layer, which is a perfectly electric conductor material. Then I have to no change. Then upper of the ground layer it should be a substrate material. Then you have to select the substrate material. I am just adding the substrate material. Here is the edit option. You can select the color of the substrate material also here. Here is a provision for color of the substrate material. Here is the option of a material. Okay, I am entering the material, then pressing the FR4. You can see the FR4 underscore Akademika which we have enter in a material window. Then I am selecting FR4 Akademika and pressing OK. Okay, you can see material in FR for Academica. Epsilon R is a 4.2 thickness. You have to enter thickness of 1.6 mm because we are using FR for material which substrate thickness is 1.6 mm, and specify loss tangent should be 0.09. Okay, now I am entering OK. Then you can see the layer 1 material type is a FR for Academica 0.0 sub. Now I have to add the upper PEC window, upper PEC layer. Then you have to press the insert key and add a metal PEC trace. Okay. Then you can choose the color of that PEC layer. Here is also options for. Okay, now I am pressing OK. Then you can see the layer 1 PEC layer which is above the layer 1 substrate layer, which is a actual layer of the patch antenna. Okay, now I am pressing apply key and then OK. Okay, now I have to draw the patch antenna which is a rectangular patch antenna. You can see here is a 5 steps of simulation or designing the patch antenna. First one is a physical structure, second one is a computational domain, third one is a discretization, fourth one is a source, and last one is a observables. Now I am pressing the physical structure. Now I am going to trace or design a patch antenna, rectangular patch antenna. You can see here is an icon for rectangle, rect strip. I am selecting that icon and tracing the rectangle. Just clicking by using left key of a mouse, you can trace a rectangle. Then after tracing a rectangle, you can see the pop-up window which is some parameters of that rectangular patch. Here you can enter the label of that rectangle. I am now entering the RMSA as a label. Here is the dimensions, which is this is a length. I am entering 29 mm is the length and 38 mm as a width. Now here is the LCS origin. LCS origin actually is the orientation of the patch antenna. Now I am entering the minus 14.05 mm as a X orientation of that antenna, and here is a minus 19 mm as a Y orientation of that antenna, and Z orientation we actually providing this is a patch antenna, so we do not require a Z orientation. Okay, now I am entering OK key. Okay, you can see the patch antenna over here. This is a substrate and this is a patch antenna. Now I am going to metal PEC trace. Then you can see the RMSA option in PEC1. This is our enter patch antenna. Now next is the embedded object set. You have to click right click of mouse and then then press insert new PEC via set, which is a source of the patch antenna, which is the setting for a source of the patch antenna. You have seen that source in a previous PPT. You can also label that source also. Now I am pressing the OK key because the settings are already provided by software. Okay. Now I am pressing OK key. Okay. Now you can see the pop-up window was stack up setting. You should okay enter the. Now I am showing the embedded set. Here is a PEC via 1. here is the some details of that PAC. Then you have to press the OK key. Okay, you can now see the PEC via 1 here option in embedded. Now you have to press you have to insert feed feed for the patch antenna. Then now I am selecting the circular feed, circular strip. I am selecting that circular strip and entering here just a circle, and you can see the pop-up window of that parameters of the circular strip here. Now I am labeling the that feed is a label as a feed. Here is a parameters. Now I am entering the outer radius of that feed is a 1.4 mm. This is because we have to achieve the proper antenna parameters. We are entering the outer radius of 1.4 mm, and you have to add the you have to locate that feed at exactly midpoint of y-axis and something 1/3 part of the x-axis. Now I am entering here minus 7.25 for x orientation, and entering minus 19 for y orientation. Now I am pressing OK. Then you can see here is a feed located at the 1/3 part of the x-axis and middle of the y-axis. Okay. Now next step is computational domain. This is already done by the software, so we have to know. We do not need to enter any settings or all that. Discretization also done by the software also. Now I am entering the source menu. Here is lots of sources are provided by software: gap sources, de-embedded sources, probe sources, and etc. Then I have to enter the probe sources because I am giving the RF signal by probe for the patch antenna. I am right click on the probe sources and insert new source. You can see the pop-up window. Here you can enter the label of that source also. Now you can see the amplitude of the RF signal is I am giving here is a 1 amplitude, and phase degree is 0. Now I am pressing OK. Then you can see the source probe source icon here. I am zooming. Here is a rectangle type shape. You can see this is a feed of the patch antenna. Now I am entering the observables. Here is lots of options for observation: current distribution, field sensors, far fields, hygiene surfaces, port definitions. Now I am entering the port definition. Right click on port definition. Here you have to select the port 1. Impedance should be 50 ohm. Then press OK. Then you can see here is a port 1 icon is printed on the display. Now I am showing the field sensor, which is used for the radiation or electric field or a magnetic field effect of the antenna at a different heights of the patch antenna. Now I am right click on the field sensor and insert new observables. Here you can see the pop-up window. Now I am setting up the coordinates of the field sensor. I am here entering 0.6 mm for a Z plane, and number of samples should be 100 x and y. Then I am pressing E field. Here is pressing E field and pressing OK. Then you can see a sensor 1. I am now next adding another sensor field. Here I am adding at 5 mm Z coordinate. At a Z axis I am adding a 5 mm Z plane for a field sensor. Here should also the 100 number of samplings. Now I am pressing OK. Now I am adding a third sensor for 100 mm. Okay. Now you can see the next options is a far field. Far field is for observing the radiation pattern of that patch antenna. Now I am pressing the insert a new radiation pattern. Okay. Then you can see the angle incident increment is a 5 degree. You can also change. Here is a provision for all these parameters. Now I am pressing the additional radiation characteristic. I am selecting directivity gain, half power beam width, and then pressing OK. Okay. Now all the procedure settings are done for patch antenna. Then you can see here is a run option, run symbol. Now I am pressing that option. You can see here is a select engine is a planar MOM. Now I am simulator mode is analysis. Here is a lots of option. After some time I will explain you how to use that options. Okay, I am running this patch antenna. You are now I am pressing yes. Okay, software is running now. You can see this is a running window. You can also see the mesh of the patch antenna. MOM mesh. You can see here near the feed of the patch antenna. The density of the MOM field should be MOM mesh is higher in a feed area. Now you can see the starting pre-computation of a spectral domain green functions in the air half space. It will take more time if suppose you have I am here inserting a sensor 1, sensor 2, sensor 3, so that it will take lots of time. You can see here the elapsed time here is a 1.1 minute. Suppose you have added the sensor 1 only, then you will get some small minimum time for simulation. Now further explanation will be done by Anirudh sir.
Now you can see this patch antenna. This patch antenna, this feed region is meshed very densely by using methods of moment. Here basically we are have to very be conscious to calculate the surface current, which requires a very dense mesh, and it is automatically done by the EM Picasso. Secondly, the EM Picasso used the Green's function formula instead of the ABC, automatic absorber boundary condition. Here we are using a Green's function formula, which is very effectively used to calculate the radiation pattern. Green's functions are very effectively can extract the information from the near field to the far field. In the sensor side, what we can see, the sensor 1, sensor 2, or sensor 3, here we are depositing some layers, and on that layer we are going to be study this kind of fields. Here we already apply the 100 points and 100 points. That's why it takes like this much time. But at the same time, the such kind of simulation softwares are having more conscious point is this memory utilization. Here you can see the memory utilization is 1.22 mbn, which is very small now in these days. If you compare with the other simulation tools, definitely for such kind of critical sensor simulation of the field sensing, specifically for the 100 sampling points, it took a memory in the GB, but the EM Cube have very much automatic algorithms which will take care about the memory utilization. And the second biggest good thing is, which is the again with the Green's function formula, which extract the surface current very successfully, and from the surface current it will calculate the near field, and from the near field data it will extract the information or the transform the information into the far field. So in the far fields we are generally putting the half surface of the air, and which is the again we are planning to calculate the radiation pattern very accurately. So even if you see the 4.5 minutes, we can tell 5 minutes times to calculate the patch antenna is not a big time to calculate very sensitively and very accurately the field distribution over the antenna, and which is the responsible to showcase the mode of your antenna. So here's the basically computing a dielectric Green's function only to accurate model your all kind of near field data as well as the far field data. Now you can see the computational domain near field distribution processing sensor number 2. Sensor number 1 is over. Now it is goes for the sensor number 2, and again apply the same configuration process and calculate this thing. It's again a predict so many things for the impedances and other parameters, and which is even here the last point is called as a data manager, which will give us the output like S11 impedance parameter, Z11, and your Y11 admittance parameters, real and imaginary both parameter you can visualize, phase as well as the magnitude in dB also you can visualize by using a data manager. So these all parameters are simultaneously calculated within a time, and in these features if you make even a critical simulation, also not taking a bigger memory but taking at the same time some kind of times. So in terms of times it will take, but in terms of memory it will not took a bigger memory scratch from your computer, and which is reasonably good for kind of small computers, which is a kind of notepad kind of things. And I am running this simulation on the notepad, which is comparatively fruitful for us. At the same time, this again we will like revise the procedure where we have to draw the physical structures, apply the feed, and the feed position is we have to calculate from the formula, but we can optimize by using this thing. And in the second demo we can demonstrate how to optimize the feed of your antenna for the good return loss things. This next is the computation demos. Here the layer stackups is we are applying. We can create our own materials, we can add own materials, and the next thing is sources, gap source, de-embedding source, probe source, short dipole, lumped element. And lumped element now these days many of the peoples are utilizing basically when the active sources are there, at that time slump source you can utilize. The plane wave excitations are there, and hygienist source. A plane wave excitation, when your antenna is a too broadband, a bigger broadband kind of things are there, that time you can utilize the plane wave excitation. If your antenna having a feed element along with some kind of lump element or lump parameter like a RLC or like kind of a pin diode kind of configurations, then you can utilize a lump element. Short dipoles is also a kind of ideal source which you can excite from outside of the antenna. This is the probe feed specially made for the 50 ohm SMA connector kind of things, which is generally utilized in most of the days for the our antennas. SMA feed 50 ohms. Then there is a gap source and de-embedding source are more popular for the inside feed kind of antenna. So in the observation also you can observe the field sensor pattern. Far field, in the far field also it is justified for the array kind of structures. You can excite this same antenna with kind of some array coefficients like Chebyshev array or binomial array. Then there is an hygiene surface you can apply, and you can see the effects for this things. And the last is the port definition. Port definition, mostly we are simulating our antenna for the 50 ohms, but sometimes if you want use some kind of quarter wave transformer of the 75 ohm or 100 ohms, that times we can use the port definitions. The periodic structure characteristic is mostly used for the antenna AMC, artificial magnetic conductor or electronic band gap structures, where the periodic characteristics are mostly responsible for the reflection coefficient plot and transmission coefficient plot. The phases are important. At the same time, the plot dispersion diagrams are important. Right now, these days, this is the very important criteria which is running in this thing. And the last is your data manager. This, it will show the readings in the CSV plot, means the Excel kind of plot, as well as the your two-dimensional plots. So now this is the it calculated successfully the second sensor problems, or second sensor, it is solved automatically within 9 minutes, and we hope that within 15 minutes it solves the three sensors, and it can demonstrate the three sensor bits.
After completion of the simulation, you can see the simulation finished successfully. Now I am pressing OK. Now here is a close. I am closing this window. Here you can see in the observables window, here is a sensor 1, here is a lots of outputs. Here also sensor 2 and sensor 3 have lots of outputs. I am now showing the far field pattern of that patch antenna. Here is the FF underscore 1 3D total. Here you can see the 3D pattern of the patch antenna. Here is the automatically calculation of the directivity of that antenna, which is given by the 4.353. Now here is a white color for a maximum power in dB and a black color for a 0 dB power. Now you can see the radiation pattern of patch antenna. Now I am showing the sensor 1, which is which we have inserted at 1.6 mm height of the origin. Here is the E magnitude of the total. Now I am pressing the properties of that E magnitude. Now I am pressing, here is a scale for a dB, and color map should be a rainbow. I am pressing OK. Then now I am pressing the top view of that patch antenna. Then you can see the rainbow pattern of that patch antenna. Here is a red color for a maximum power for dB. Then here you can see the feed area is showing the red color, and after that you can see here is the yellow color, which should be around the 32 dB, which is the width of that patch antenna. Here also the width of that patch antenna. Now I am showing the sensor 2 H magnetic field magnitude of the patch and that patch antenna. Now I am pressing the dB rainbow. Okay. Here you can see the magnetic field and electric field should be opposite in all the parameters. In previous section you can see here is the electric field at a high power density. Now you can see here is the high magnetic field is here which is always at a 90 degree in electric field. Now I am showing the sensor to output, electric field magnitude dB rainbow. Now I am pressing OK. This sensor to output is just above the 5 mm of that patch antenna. Now you can see the rainbow pattern of that patch antenna. Here is the width of the, you can see width of that patch antenna. Here is the red for high power. Now I am showing you the third which we have pressed the third sensor frame just above the 100 mm of the patch antenna. Now you can see here is a red uh, portion which indicates the high power in dB in electric fields, and then the radiation pattern and electric field pattern in rainbow section. Next portion will be explained by Anirudh sir.
Now we can see the pattern quickly in the XY plane, basically two-dimensional pattern. If we see in the two-dimensional pattern, we can see the plot, HPW in the polar plot. So here is the polar plot XY and say plot, okay, and this is the in XY direction, and and here you can see this is the actually a directive pattern you can achieve, and this is the some kind of small side lobes are happen in this area, and this is the mainly the directive area. And here same we are comparing with our ideal pattern. Here is the your RMS antenna, here is the transmitting antenna. Here you can see the main lobe with the small kind of back lobes are created over here, and here is small pinches there due to this chairs and the others environments is created. But you can see the half of the pattern means this area it is comparatively matched with your simulation window. Even in simulation window this is the purely match, and this is the back lobe same created in the practical as well as the simulation. Thank you.